In this example, we consider a cantilever beam subjected to an arbitrary load. This case is certainly not tabulated, and the reason I like to look at this case is A, because it gives us a pretty useful general solution. B, it shows that superposition may involve not just a finite number of simple solutions, but an infinite number. So I have my standard cantilever beam of length L, constant bending stiffness EI, and it is loaded by an arbitrary distributed load prescribed by a function q of x. And my task is to determine the deflection at the tip of the beam. So I would like to start by considering a small element of length delta A located at the distance A. And of course, this elementary load could be thought as a concentrated force of magnitude Q of A times delta A. But for a concentrated force, we have a table. And in this table, delta B is the displacement of the tip. And in order to exploit this table, all we have to do is to replace P with Q of A times delta A. So what we have here is the displacement of the tip, which I denote delta. I draw the subscript B, induced by the elementary load Q of A times delta A. The reason I use A here is because A appears in the table, and so I can rewrite this expression that kind of singles out Q of A times delta A at the end, and whatever is left comes in the front. Now, I will view this as my tabulation. Let me view my table now. And now I will write as Q of X delta X rather than Q of A delta A. I like my X's rather than A's as integration variables, but of course it's a purely matter of cosmetics. Now, if I look at the entire beam loaded by load, which is a superposition of elementary gaps. And now then I can say that my delta is the sum of the deltas induced by elementary loads of this type. Now I can take the expression for delta, elementary delta, and I obtain this Riemann sum. Of course, I can think about this Riemann sum as a superposition, but of course, the Riemann sum is closely related to the integral. And not surprisingly, all I have to do is to replace delta x with dx, and instead of the sum, I'll write integral from 0 to L. The remaining terms are the same in the sum and the integral, and this gives me the expression for the deflection of the tip in terms of an arbitrary Q of X. A very general result. So let's see how it works. So I will be using this formula, and first I will look at uniform load. So Q of X is simply Q naught. I substitute q naught instead of q of x. And you could see that I can pull out constant terms. And what I have here is a cubic polynomial. So I expand this parenthesis, and then I integrate term by term, and at the end I obtain this expression. This expression is actually the first table for the cantilever beam, which says that the displacement of the tip due to a uniformly distributed load Q naught is given by Q naught L to the 4 over AKI. So this confirms our integral expression. Next, let us do something that is not in the tables. I will choose a power law load. It is given by this expression, where Q of n is a constant, and so is n. So could be constant, could be linear, could be quadratic, whatever n you wish to choose. We send it through this grinder, and let us see what we have. Now Q of x is replaced by Q sub n x over L to the power n. But we're still integrating polynomials, all right? And the answer is here, right? But all we have to do, we have to integrate powers of x, which is very simple. And we can also check that the previous case, n equal to 0, gives me 9 divided by 12, which is 3/4. 3/4 divided by 6 gives me 1 over 8, which was the result from the previous slide. Now we can use superposition once again. Now I would like to look at a much more general load. It's a polynomial load which represents literally any smooth function. And so if I choose this load, then I can think about, then I have n elementary power law loads. How do I proceed? I say that due to one term, which is q n x over L to the power n, the deflection of the tip has been computed on the previous slide. Now the superposition is over n terms in this series, and what do I get? I get that the displacement of the tip is the superposition of the displacement, and all I have to do, I'll take this expression, I take the sum, inside the sum I'll put the terms that depend on n, which means that these guys are outside of the sum, the rest are inside, and that's the answer for an arbitrary polynomial.